So we're actually rolling back around. This is what would be semester 1. So we're starting the cycle over again. So we're going to start off with basic measurement conversions. And so it all works off of the idea of converting with fractions. If I have a fraction like 3/4 and I need to change the denominator, rename it, and I need it to be 20ths, how do we do that? Times 5, yep. And technically what we're multiplying by is 5 over 5. You've always been told if whatever you multiply the denominator by, you multiply the numerator by. Well, the reason for that, of course, 4 times 5 is 20, 3 times 5 is 15. The reason for that is what this is, 5 over 5 is just 1. And when you multiply or divide something by 1, it doesn't change the value. It changed the appearance. 3/4 and 15/20 look different, but they have exactly the same value. So this structure, the 5 over 5, is called a unity fraction. And it's a real powerful tool in math because it allows us to do just what we did. We changed the appearance of something without changing its value. And so the technical definition of a unity fraction is just a fraction where the numerator, or the top number, equals the denominator. So when we get into measurement conversions, this looks a little bit different because, well, it's not as obvious that the numerator and denominator are equal to each other. Slide over a little bit here. So let's start out with one that you all know how to do. If I were to ask you to convert 4 feet into inches, of course, most of you could just tell me that that's how many inches. 48, yeah. If you didn't know that, how would you make the conversion? Well, we start out with our 4 feet. We make it into a fraction by putting it over 1, because everything's easier when you make it into a fraction, right? But it actually is. And then the unity fraction takes the form of a conversion factor. And so what we look for is we're going to use an equivalency. So an equivalency involved here with feet and inches. Of course, we know 1 foot equals 12 inches. Good. So we use that in that unity fraction. Now we're getting rid of feet. And if you remember way back, one of the rules with fractions is you can cross-cancel common factors. So we can put feet down here so that they will cancel out. Then we use 1 foot equals 12 inches. Now this does not look like it equals 1, but it does. The numerator and denominator have the same value. 12 inches is equal to 1 foot. So when we go ahead and calculate with that, the feet cancel out. 4 times 12 inches is 48 inches. 1 times 1 is just 1. 48 inches divided by 1 is 48 inches. Well, we all knew that one already. So let's look at one that you might not be so familiar with. If I have 99 feet, and I ask you to convert it into rods. Rods doesn't get used much anymore. The main reason it's survived in our measurement system is land surveying. Most of your land surveys are done in rods and chains. But if I tell you that 1 rod equals 16.5 or 16.5 feet, we can do that conversion. We really don't need to know a whole lot about the units themselves other than that equivalency. So we do the 99 feet over 1. We're getting rid of feet again, so feet go on bottom. 16.5 feet is equivalent to 1 rod. The feet will cancel out. 99 times 1 rod is 99 rods. 1 times 16.5 is 16.5. Now up here, the bottom number was 1, so we didn't have to do anything. When you divide by 1, it doesn't do anything. Down here, we do have to divide out 99 rods divided by 16.5 is going to be 6. You got it. So that's 6 rods. We're not going to spend a lot of time dealing with converting within the standards. I shouldn't call it the standard system. The U.S. customary system, they call it now. They've started referring to the metric system as standard. How many of you work mostly with the metric system now at work? Not anybody yet? Mixed yet? Okay. There was a huge push in the late 80s and early 90s. Most companies were like going mostly metric. And then 15, 20 years ago, there was a push and it went back the other direction to where standard, again, I got to stop calling it standard. U.S. customary measurement is now back in style. There are several international companies. I believe 3M, if I remember right, was one that announced a few years back that everything they were going to produce, even whether it's produced in the U.S. or abroad, was going to be done in metric units. And they figured in that first year it saved over $8 million. Just because when you engineered something, you didn't have to design it in both units. You didn't have to design it so that it could be, you don't want something to be 8 centimeters and 2.789, 4 inches or whatever. You want the units to be somewhat reasonable in both units. So it did cost a lot of extra design. Also, the fact that sometimes the conversions were sloppy, and so you'd produce parts that didn't quite fit real well. And so the waste was higher that way. So going to strictly metric units saved them a lot of money. And other companies that do international business are kind of going towards that now. Heck, I remember, I'm going to date myself here, but 36, 37 years ago when I was in middle school, my middle school science teacher preaching to us, within 10 years, the U.S. is going to be on the metric system. Didn't happen. It will happen eventually, though. So anyway, the big deal for us doing these conversions is to convert between standard and metric. If you have a 40-foot cable that you need to replace, and now you can only order it in meters, you can look up the relationship between meters and feet. You might find that 1 meter equals 3.28 feet. So then you start out, take your 40 feet, put it over 1, and then what's going to go in our conversion factor? I always start with what goes on bottom. 3.28 feet on bottom. You got it. My pen's not working. There we go. And then, of course, on top is the 1 meter. So the feet will cancel. 40 times 1 meter will be 40 meters. On bottom, 1 times 3.28 is 3.28. And we divide, giving us 12.19520, depending on what our desired precision is. You might have a counterweight that currently weighs 18 pounds. You go to replace it, you can only get it in kilograms. The standardly accepted conversion is that 1 kilogram is 2.2 pounds. That's severely rounded off, but that's what they usually use. So we start out with our 18 pounds, put it over 1. And again, now what's going to go in our conversion factor? What's going to go on bottom? 2.2 pounds, good. And on top will be the 1 kilogram. So once again, the pounds will cancel out. 18 times 1 kilogram is 18 kilograms. On bottom, 1 times 2.2 is just 2.2. And then we have to divide out. So 18 kilograms divided by 2.2 pounds. We get 8.18 kilograms. If you have a tank that is 400 gallons, again, you need to replace it. We're going to have to replace it in liters. Find the relationship. 1 gallon is 3.785 liters. So again, you start out with the 400 gallons, put it over 1. In our conversion factor, what's going to go on bottom? Careful. We're getting rid of gallons. So the gallon goes on bottom. Yep. So the 3.785 goes on top. And that's why I always start out with the bottom number, because I know that whatever goes down here has to be the same unit as this one. So then we can match them up. So now on bottom, 1 times 1 is 1, so we know we're not going to have to divide. We just have to do the 400 times 3.785 gallons, or liters, giving us 1,514 liters. Not so bad? So really the key is just being able to find the equivalencies. How many of you deal with really precision measurement as far as weights are concerned? Not a whole lot? You don't get down into drams or grains or anything on stuff you do? We won't do any conversions with it, but there are units that a lot of people don't realize that 1 ounce is 16 drams. And 1 pound, 7,000 grains. You may never have heard of drams. A dram was one of the original apothecary units. You might be prescribed 1/8 of a dram of a medication or whatever. Grains were also an apothecary unit. You might be given an 800 grain medication or something like that. If you're familiar with guns and shooting, you've heard of grains. Your powder and your bullets are measured in grains usually. It is one that is actually was common enough that it got absorbed in the metric system. Not well, but they did absorb it into the metric system, where 1 gram equals 60 grains, and 1 grain equals 15 milligrams. If you do the math there, 60 times 15 is 900. There's 1,000 milligrams in a gram. So that's why I say it was not absorbed into the metric system well. It's actually like 15.8 milligrams and 62 point some grains in a gram, but they rounded them off because the metric system likes nice round numbers. But they're used a lot, especially in the medical fields. So they had to absorb them into the metric system to keep certain populations happy, I guess would be the way to put it. The other reason using these conversion factors is handy, well, let's just throw an example out there. If I were to tell you guys that I can throw a baseball 90 feet per second, would you believe me? At this point, I'm not sure if I can even throw a baseball, but let's go back 10 years. And I told you that 10 years ago I could throw a baseball 90 feet per second. Is that fast? But what unit are we used to measuring speed in for baseballs and everything else? Miles per hour. So I need to convert that into miles per hour somehow. Well, whenever we see a unit like this, that's a rate with the dual units in it, it's actually comparing 2 numbers. That really means 90 feet over 1 second. And we can use these unity fractions or conversion factors to convert both units. Doesn't matter which one we start with. I'm going to start with the top one to convert feet. So to get rid of feet, I'm going to put it on bottom. What units is feet getting converted to? Miles, right? What's our relationship between feet and miles? How many feet in a mile? 5,280, 5,280. So now the feet will cancel out. Currently, we're in miles per second. So we have to get rid of the miles are appropriate. We need to get rid of the seconds. Now, seconds are on bottom here, so to cancel them out, seconds have to go on top. Now, we need to get to hours. Probably should go through minutes first. 1 minute is how many seconds? 60. So the seconds cancel out. We still have to get rid of minutes. Now, again, minutes are on bottom, so to cancel them, we put them on top. 1 hour, of course, is, once again, 60 minutes. This is one that comes up often enough that I just have memorized 1 hour is 3,600 seconds. So that way I don't have to go through the 2 steps of converting it. I can just go straight from seconds to hours. So anyway, my units have all canceled out. I have miles on top and hours on bottom. Every other unit is canceled out. That's what I want, miles on top and hours on bottom. So I have to go through and multiply. On top, I have 90 times 1 mile times 60 times 60. Oh, what is that? 324,000 miles. On bottom, I have 1 times 5,280 times 1 times 1 hour, so 5,280 hours. And then we have to divide that out. So 324,000 divided by 5,280. It helps if I put in my division. Gives us 61.36 miles per hour. That one always usually surprises people the first time you do the conversion because you'd think feet per second, miles per hour would be 90 feet per second sounds really fast, but it is only 61 or 62 miles per hour. And just for the record, 10 years ago, I probably still couldn't throw that fast. 25 years ago, maybe. Now I don't know if I could throw a baseball from here to the door anymore. My shoulders are so bad. Getting old sucks. So anyway, converting those dual units or those rates like that is something that happens quite a bit. Let's say you have something that comes to you that is listed as 1.2 ounces per cubic inch. So we're going to start out with, and we want to convert it, of course, we're used to things being in pounds per cubic foot. Oops, cubic, not square. So we start out with our 1.2 ounces over 1 cubic inch. Ounces are on top, so we'll get rid of them first. Take the ounces. We're going to convert ounces into what? Pounds. The bigger unit is the pound, so 1 pound equals how many ounces? 16. Side note, you'll always see that whenever I write pounds with a number in front of it, I tend to always underline the LB. It's an old engineer's trick of, is that 521B or is that 52 pounds? Underlining the LB tells you that that is pounds. It's just like the reason I cross my sevens. So the ounces will cancel out there. We still have to get rid of cubic inches. So we might need to talk about this a little bit. Putting the cubic inches are on bottom, so we put them on top. Going to cubic feet. Oops, I keep writing 2 for cubic. Inches to the third, feet to the third, cubic inches to cubic feet. We know that 1 foot equals 12 inches. Do you know how many cubic inches are in 1 cubic foot? Okay, good. That's one that I figured we'd have to take a look at. So the definition of a cubic foot is 1 foot by 1 foot by 1 foot. What's that? You're a little bit off. You're halfway there. 1728. You got it. Yeah, so it's 12 inches by 12 inches by 12 inches. So yes, if you do 12 inches times 12 inches times 12 inches, that does come out to 1,728 cubic inches. 864, number you had memorized from somewhere? No? I just did it quick? Okay. So 1 cubic foot is 1728. So the cubic inches cancel out. On top, we'll have to multiply the 1.2 times 1 pound times 1728. So 1.2 times 1728, 2073.6. That's pounds. On bottom, 1 times 16 times 1 cubic foot is 16 cubic feet. So we have to divide that out. We're going to divide by the 16 with 129.6 pounds per cubic foot. That is the density of some of your lighter metals. I mean, that's right around the density of aluminum. You might have something listed as a consumption rate of 3.2 fluid ounces per square inch of surface area. And let's put this into a context. Let's say we need to cover 1,800 square feet. We really don't want to be measuring out fluid ounces here, right? So we're probably going to be looking at gallons. Well, our units would most likely be used, probably using gallons per 1,000 square feet or gallons per 100 square feet. To do this conversion, we are going to have to just convert to gallons per square foot. Then we'll worry about the per 1,000 square feet later. So 3.2 fluid ounces over 1 square inch. So we have to get from fluid ounces to gallons, and this is going to take a few steps. Fluid ounces are on top. We're going to put it on bottom. If we go up the ladder, what's the next unit bigger in our capacity scale from fluid ounces? We have a couple of options. We can go to cups. 1 cup is 8 fluid ounces. So the fluid ounces have canceled out. Oh, we don't want to stop at cups. So cups are on top. I'll put cups on bottom. What's our next biggest unit from a cup? Pint. 1 pint is 2 cups. Cups are gone. Getting rid of pints, we would go to, what's next? Quart. 1 quart is 2 pints. Get this out of the way. Then the next one is one where I catch people just because they get in a little bit of a groove. Next bigger unit, of course, is the gallon. Oops, I gotta get rid of my quarts. I'll put quarts on bottom, gallons on top. 1 gallon's how many quarts? 4. Good. The way to remember that is quart is actually short for quarter gallon. That's where the name came from. So 4 quarts in a gallon. So the quarts have canceled out. We now have gallons on top, which is what we want. We need to get our square inches into square feet. Square inches are on bottom, so we put them on top to get rid of them. Square feet on bottom. 1 square foot's how many square inches? So it'll be the same concept, 1 foot by 1 foot. 12 by 12 is 144. You got it. So the square inches have canceled out. So on top here, we have 3.2 times 144. Give us 460.8. Go away. And the only unit left on top is gallons. On bottom, we have some multiplying to do. 1 times 8 times 2 is 16, times 2 is 32, times 4 is 128 square feet. So we're going to divide that out. 460.8 divided by 128. We get 3.6 gallons per square foot. It's quite a healthy coverage. That's what I get when I make it up an example on the fly. So if you wanted that to be per 1,000 square feet, all you would do is you'd set up a proportion, 3.6 gallons per 1 square foot or 1 square foot. If I want it to be per 1,000 square feet, to get from here to there, you're multiplying by 1,000. Up here, you multiply by 1,000. So it's 3,600 gallons. One that I used to run into quite a bit. Let's say we have a pump that is rated at 4,000 gallons per hour. Most pumps are rated in what units? CFM. CFM stands for cubic feet per minute. A good industrial pump is usually between 8 and 12 cubic feet per minute. So if you're looking at this 4,000 gallon per hour pump, sounds like a pretty good volume, but is that a good pump? I'll put our 4,000 gallons over 1 hour. It's a terrible pump. Yeah, it's a really small one. We get rid of our gallons, so they go on bottom, going to cubic feet. Anybody know how many gallons are in a cubic foot? If you think of a 5-gallon bucket, would you say that that is about a cubic foot, or is that smaller or larger than a cubic foot? It's actually significantly smaller. Most people would say it's pretty close to a cubic foot, but it's only about 9 inches on the bottom, and being a circle, you lose a lot of volume in the corners. There are actually 7.5 gallons. Technically, it's 7.48, but I've always used 7.5 for every application. It's been accurate enough. So I'll cancel out the gallons. And then, of course, we have to change from the hours to the minutes. Hours are on bottom, so we put them on top. 1 hour is 60 minutes. So the hours cancel out. On top here, we have 4,000 times 1 cubic foot. On bottom, 1 times 7.5 times 60 minutes is 450 minutes. So we have the 4,000 divided by 450, get about 8.89 cubic feet per minute. So that is on the very low end of your standard range. the one conversion that doesn't fit with all of our other conversions, that being you guys are doing welding in this unit is going to be a pretty common conversion for you, is temperature. And so let's look. We have our Fahrenheit scale as our standard scale. 25 years of teaching measurement conversions. You'd think I could remember how to spell Fahrenheit with looking at my notes, but I can't. And the metric equivalent is Celsius. The two big benchmarks that we use for temperature temperature at which water freezes and boils. You got it. Now, these temperatures, by the way, should be noted that it's at standard atmospheric pressure at sea level. In the Fahrenheit scale, what temperature does water freeze at? Oops, boils at 212, yep. Freezes at 32. Actually, most groups don't remember the 212 anymore, so I'm kind of impressed. For Celsius, what temperature does water freeze at? 0, and it boils at 100. Because of that 100 degrees between freezing and thawing, the Celsius scale is sometimes referred to as the centigrade scale. Just because centi means 100, grade means division. So if you ever hear, 13 degrees centigrade, they just mean 13 degrees Celsius. Now, like I said, these are temperatures at standard atmospheric pressure. You guys have done the atmospheric pressure calculations on your pump calculations and stuff like that. If you go to some place like Denver where you're high above sea level, atmospheric pressure is considerably lower. Water will boil at a considerably lower temperature. One of my best friends used to like soft-boiled eggs, and he had it timed down to like the second. I believe it was like 3 minutes and 20 seconds. You dropped it into the boiling water, and it was just how he wanted them. He went to Denver, boiled the water, threw it in for 3 minutes and 20 seconds, came out, and it was just about raw because it was about 15 degrees cooler that water boiled at the lower pressure. So he had to figure it all out, had to boil it longer to make it work. So anyway, with temperature, the problem we have is there is no common 0 point. In every other unit of measurement, there is a 0 that is common no matter what unit you're using. 0 inches equals 0 centimeters equals 0 kilometers equals 0 miles. 0 pounds equals 0 kilograms equals 0 ounces, and so on. But in temperature, 0 degrees Fahrenheit does not equal 0 degrees Celsius. So we cannot use that simple conversion factor, that unity fraction, to convert. So what we have to do is we have to create a formula, and that formula involves two things. First is the difference in 0 point. So for Fahrenheit, it's at 32 degrees. For Celsius, it's at 0 degrees. There's a 32 degree difference. So when we do these conversions, at some point in our conversion, we're either going to have to add 32 or subtract 32, depending on what direction we're going. The second thing we have to consider then is the size. From freezing to boiling, 212 minus 332 is 180 degrees in the Fahrenheit scale. In the Celsius scale, we already said that's 100 degrees difference. So there's that ratio. We have to account for the size of a degree. And depending on how you put it, it's 180 over 100, which if you divide that out, both will divide by 20, is 9 over 5. Or the other way around, 100 over 180, which is 5 over 9, depending on what direction you're going again. So if we are starting out in degrees Fahrenheit and converting into degrees Celsius, we start out in the temperature in degrees Fahrenheit. We subtract the 32 to get the common 0 point. And then once we get that difference, that's why I have parentheses around it, we multiply by 5/9 to convert that down to the size of a degree Celsius. So let's take a pretty standard one here. 98.6 degrees Fahrenheit is human body temperature. Let's convert that to degrees Celsius. So we're going to put that in for F. So C equals 5/9 times 98.6 minus 32. Order of operations, what do we have to do first? Parentheses. 98.6 minus 32, bless you. 66.6, you got it. Equals, down to 5/9 times 66. It's 37. So on your calculator, if you have a fraction calculator, you can use it. Otherwise, if you're using a cell phone calculator, it's just 5 divided by 9 and then times 66.6. Get 37. So human body temperature is 37 degrees Celsius. If we're going the other way, from degrees Celsius into degrees Fahrenheit, we start out with our temperature in degrees Celsius, and we have to exactly reverse this process. Well, the last thing we did here was multiply by the 5/9. So over here, the first thing we're going to do is we're not going to divide by 5/9. Instead, we're going to multiply by 9/5. And then after we've done that, we're going to reverse the subtracting 32 by adding 32 to it. So if you wake up in the morning and the weather forecaster says it's going to be, the colors are mixing on me, it's going to be 20 degrees Celsius today. Are you wearing jeans and shorts and a t-shirt, or are you wearing boots and mittens? You'd be changing, find an American channel. So to be honest, the whole metric to customary units changing over to metric, my viewpoint, my belief on it is, I was in middle school. I was born in 73, and I was really kind of the first generation where they really pushed the metric system in school. People that are older than me didn't get a lot of the metric system in school. And if you look at who's in power in this country, most of your corporate CEOs are in their 60s and 70s. They're just a few years older than me. They're not familiar with the metric system. So I think what it's going to take is it's going to wait for that group to retire and my age group to move up and the younger age groups to move up before the metric conversion really takes place. The U.S. has actually left it. Other countries have just said, we're switching on this date period. The U.S. has left it up to individual regulatory agencies. In the United States, you cannot buy a quart of alcohol or a pint of alcohol. You cannot buy a pound of gunpowder. You cannot buy a pound of tobacco. You have to buy a 3/4 liter of alcohol. You have to buy a 1/2 kilogram of gunpowder. Because the ATF, Alcohol, Tobacco, and Firearms, switched over to the metric system like 20 years ago. Actually, a little bit longer than that now. It's been close to 30 years ago now. Other agencies haven't followed. I think the FDA is getting close because if you look at your soda bottles, everything is labeled fluid ounces, but also milligrams or 0.5 liters or whatever. It's labeled in both units. I think that's going to be the next agency to go. Probably the most resistant one is going to be Department of Transportation. Because if we went out on the street out here and pulled down the sign that said speed limit 55 mph and put up a sign that said speed limit 88 kph, same speed, but people probably get home a little quicker tonight. So to make this conversion, we put the 20 degrees in for C, so it's 9/5 times 20 plus 32. And so order of operations, what's the first thing we have to do here? 9 divided by 5 times 20 is it 36? Yep. Perfect. Then we do the 36 plus 32, 68 degrees Fahrenheit. That's almost a perfect day for me. The last thing that we need to know these conversions for is if I have (5 feet 8 inches plus 7 feet 6 inches. If we have to do any sort of calculation with them. Just like any other operation, we start on the right, work our way backwards. What's 8 plus 6? 14 inches. That, of course, is bigger than a foot. It breaks down into 1 foot and how many inches left? 2. Good. So, again, just like any other operation, we keep part of it and carry part of it. We keep the 2, we carry the 1 foot. 1 plus 5 plus 7 is 13 feet. We might have 6 pounds, 13 ounces, plus 4 pounds, 9 ounces. Again, we do the same thing. We start at the end of the number at the right and work our way backwards. 13 plus 9 is 22. That's bigger than a pound. It's 1 pound and how many ounces left? 6. There we go. So we keep the 6, carry the 1. 1 plus 6 plus 4. It's 11 pounds. Oh, let's have a little fun. If you haven't learned yet, anytime a math teacher says, let's have a little fun, it's probably not a good sign. This one's not so bad. Again, we start at the end and work our way backwards. What's 9 inches plus 10 inches? 19 inches. So that's bigger than a foot. That's 1 foot with how many inches left over? 7, yep. So 1 foot, 7 inches. So we're going to keep the 7 inches, carry the 1 foot. 1 plus 5 plus, or 1 plus 2 plus 2, of course, is 5. I gave that away. Which is more than a yard. It's 1 yard and how many feet? 2 feet. So we keep the 2 feet, carry the 1 yard. 1, 4, and 3 make 8 yards. So 8 yards, 2 feet, 7 inches. Just to keep you on your toes. So we haven't talked about how many yards are in a rod. So I tell you that 1 rod is 5.5 yards. So we do this this operation here. We're going to add 4 yards plus 3 yards is 7 yards. We know that's bigger than a rod, so we're going to carry 1 rod, and we're going to subtract the 5.5 that was the 1 rod, and what's left? 1.5, right? Then on top, we got 1 plus 3 is 4, plus 5 is 9 rods. If we need to subtract, 7 feet 3 inches minus 4 feet 10 inches. Again, we still start on the right, work our way back to the left. 3 minus 10 can't be done, so we're going to need to borrow. 7 feet becomes 6 feet. The 3 inches becomes how many inches? 15, good. A lot of groups will yell out 13 first there. It's 12 inches in a foot, so we got to add 12 to it. 15 minus 10 is 5 inches. 6 minus 4, 2 feet. Or if we have 7 pounds, 3 ounces, minus 2 pounds, 14 ounces. Bless you. Again, we can't do the 3 minus 14. We got to borrow from the 7. That's going to be 6 pounds. How many ounces is this going to be? 19. There we go. And so we subtract 19 minus 14 will be 5 ounces. 6 minus 2, 4 pounds. When we go to multiply, let's do 5 feet 9 inches times 6. So this is if we need pieces that are 5 foot 9 inches long and we need a total of 6 of them. How long total, what total length do we need? Well, we still start out on the right and work our way back to the left. 6 times 9 is 54 inches. Now we have to figure out how many feet we can get out of that. 4 feet. 4 times 12 is 48 inches. So how many inches are left? 6. And then we carry the 4 feet. 6 times 5 is 30, plus the 4 we carried is 34 feet. So we need a total length of 34 feet, 6 inches. If we need 9 pounds, 12 ounces, and we're going to need 5 of those. 5 times 12 is 60 ounces. Once again, we need to figure out how many pounds we can get out of that. Well, 4 times 16 is 64, so that's too big. 3 times 16 would be 48. So we can get 3 pounds out of it, so we'll carry the 3 pounds. How many ounces do we have left? 12. Good. 60 minus 48 is 12. Now we do the 5 times 9 is 45, plus the 3 we carried, 48. So it would be a total of 48 pounds, 12 ounces. Finally, division. Let's say we have something 29 feet, 8 inches long, and we have to cut it into 4 equal pieces. 4 goes into 29 how many times? 7? What's 7 times 4? 28. So there's 1 foot left over. Before I can bring down the 8 inches, I do have to convert the feet into inches. Of course, 1 foot's 12 inches. Now I bring down the 8 inches. 8 plus 12, we have 20 inches to work with. What's 20 divided by 4? 5 inches. If I have something 26 feet, 3 inches long, and I need to cut it into 7 equal pieces, how many times does 7 go into 26? 3. 3 feet times 7 is 21. We subtract, we have 5 feet left over. Good. Before I bring down the 3 feet, I have to turn the 3 inches, I should say. I have to turn the 5 feet into how many inches? 60. Now I bring down the 3 plus 60 is 63 inches. And 63 divided by 7 is 9 inches. What do you think? Okay, so what I'm going to do is I'm going to give you guys a little bit of work time and a break. So I'm going to give you the work. So our next section involves more conversions with our measurement. but it deals with proportions. And so this is not a real common one. That's why we only have a few problems on it. But we do run into rates. We've already converted some rates, but rates that are set up like this where we have 210 pounds in a 3.5 square foot area. How many ounces would that be in a 15 square inch area? And if it's not something we have to do over and over again, it's simplest just to do the conversion once in a proportion like this rather than converting the rate. When we have something like this, obviously in a proportion, whatever units are here should be the same over here. And down on bottom, same thing. Whatever units are on the left should be the same as units on the right. So we have to convert one of the units. Usually it's easiest to convert to the smallest unit. So I'm going to take the pounds here and convert it to ounces. Of course, there's how many ounces in a pound? 16. So I'm going to take my 210 times 16. And yes, I'm going to be sloppy with my conversion and not write out my conversion factors. But we get 3,360 ounces. And then I'm going to convert my square feet into square inches. Anybody remember how many square inches are in a square foot? 144, good. And again, that's just 12 times 12 or 12 squared. So 3.5 times 144 is 504 square inches. Now we have the same units in both. And to solve a proportion, it's just cross, multiply, and divide. So 3,360 times 15 divided by 504. Giving us 100 ounces in 15 square inches. I couldn't have planned that one if I tried. Any questions on what we did there? So the same over here in the second one, only we're starting out with the smaller units. We still need to convert the bigger units to the small units to make this work. So gallons are going to get converted to pints. Of course, we're probably going to go from gallons to quarts first. So we start out with the 6,200 gallons. How many quarts in a gallon? 4, so times 4. And then how many pints in a quart? 2, so times 2. So 49,600 pints in that 6,200 gallons. One thing to always remember when you're doing these, I learned when I was very early on to estimate my answers before I punch anything in the calculator. If the units are getting smaller, the number has to get bigger. So when you're doing this, gallons got smaller to get to pints. The number itself had to get bigger. So we knew we at least went in the right direction there. And then when I do my cross multiplying and dividing, the answer I'm going to get here is not going to be hours. It's going to be minutes. We'll have to convert it back to hours when we're done. So now we can cross multiply and divide. 3 times 49,600 divided by 17. So 49,600 times 3 divided by 17. So we get 8,752.94 minutes. And what do we do to convert that back to hours? Divide by 60. Yeah, good. The unit's getting bigger. Hours to minutes is getting bigger. The number gets smaller. So it's 145.88 hours. If it's metric, the conversions are a little bit easier, but sometimes it's harder to do these problems because the conversions are easier. So the bigger unit is the kilogram, so I want to convert to the smaller unit, which will be the gram. A kilogram is 1,000 grams. So this is 190,000 grams. So the answer I'm going to get here is going to be in centimeters squared, and then we'll have to convert it to meters squared. So you cross multiply and divide. 7 times 190,000 divided by 65. Now we get 20,461.54. Of course, that is centimeters squared. It's going to be whatever that unit is. Now, to get from centimeters squared to meters squared, just like with inches, square inches to square feet, we have to be careful. 1 meter is 100 centimeters. So that means 1 meter squared is going to be 100 squared, or 10,000 centimeters squared. So as we saw with the customary units, when we square the units, go from meters to meters squared, the number, the conversion factor has to be squared too. 100 squared gives the 10,000. So we're going to a bigger unit. The number gets smaller, so we're going to divide by the 10,000. So this is going to be 2.05 meters squared. This last one's actually a spreading formula. We use it for fertilizer, chemical disposal, whatever. This is actually a chemical disposal example. You're allowed to put up to 4.2 pounds of this over a 25 square foot area. If you needed to dispose of 3.7 tons, how many acres would you need? So again, the smaller unit here for the top number is pounds. So I'm going to convert my tons into pounds. How many pounds in a ton? 2,000. So 2,000 times 3.7 is 7,400 pounds. I don't think it gets used in anything anymore, but there's something called a long ton out there that's 2,240 pounds. It used to get used in shipping because it was the weight of the cargo plus the container. So now, when we cross multiply and divide, what we're going to get down here is going to be square feet, and we'll have to convert it to acres later. So 7,400 times 25 divided by 4.2. We get 44,047.62. So this is not one we do very often, so I'll set up the conversion factor. Put the 44,047.62 square feet over 1. Anybody happen to know how many square feet are in an acre? 43,560. We do the cancel out the square feet. So this is going to be 44,047.62 acres on top. 43,560 on bottom. So obviously we have to divide that out. Giving us 1.01 basically acres. A little bit of history for you. We mentioned the rods as your surveying area. The other survey area is a chain. One chain is 4 rods or 66 feet. So one square chain, if you square 66, you get 4,356. The acre is just 10 square chains. That's where the 43,560 comes from. Okay, so that's why we divide things into 40s, by the way, because it's 20 chains by 20 chains. Enough of that. So next we're going to move on to our actual welding and metallurgy formulas. One thing we're talking about, we got to just do a quick basic percent. When we do a basic percent calculation, let's say I have you, like, I'm just going to do the whole sentence. We're not going to have missing numbers here. 32 is 80% of 40. The way we would put that into a calculation, we could use it. There's two ways we could do it. We could use a proportion, which I think usually gives us fewer mistakes, but most people have to use paper to set it up to see where things line up. You start with the percent. 80% means 80 out of 100. 32 out of 40, put the 32 over 40, and then whatever piece is missing, you cross, multiply, and divide. So if this is asking $56 is blank percent of 80, the percent is missing, so it's blank over 100 equals 56 out of 80. To find the percent, you cross, multiply, and divide. So whatever two numbers are diagonal, you multiply. 100 times 56 is 5,600. And the third number you divide by. So divide by 80 gives us 70. So 70 over 100 is 70%. The other way you could do it, that some of you might be more familiar with, is the rate method. Problem with the rate method is it involves you to see what pieces you have, and you have to decide, am I going to multiply? Am I going to divide? What operation do I have to do here? So for this problem down here, we don't have the percent. So we do the 56 divided by 80 equals 0.7, and we convert that decimal into the equivalent percent of 70%. If I had blank is 35% of 160. For the rate method, I have to turn that 35% into a rate or a decimal form. So that's 0.35. And then since this is the base amount, it's the larger amount, I do 160 times 0.35, which I believe that gives me 56. If I was using the proportion method, it's just 35 over 100 equals blank over 160. I cross multiply. 35 times 160 is 5,600. Divided by 100 gives me 56. So whichever method works easiest for you, a lot of it depends on what you were taught. In the last 20 years or so, the proportion method's been more popular. Before that, it was the rate method. I was taught the rate method. It's a lot quicker to punch in the calculator, but you also have to make that decision. Do I have to divide? Do I have to multiply? Whatever here. If we need to do more with percents, we can come back and do that later if you need a review on percents. But I just wanted to do that quickly because one of the things we look at in welding is percent of penetration. So let's say that we have 3/8 inch steel and we need 80% penetration on our weld. Have you guys talked about weld penetration yet? Not really? Okay. So if you're welding two pieces together, best practice is have the ends slightly beveled. Leave a small foot between the bottom pieces of the points. And then your weld would penetrate into the metal a certain percentage of the thickness. You don't want it to come out the bottom or it'll bubble the bottom. So you don't want, ideally it would be 100% penetration with nothing pushing through. Not possible. So you want to, depending on your weld, sometimes you want to hit that 80 to 90%. Other times you're looking for like 50%. You're going to weld it from both sides. Certain materials you can't do that with. So anyway, 80% penetration. So 80%, I'm going to set it up with the proportion. So it'll be 80 out of 100. Now the 3/8 is the full amount. That is the 100%. That would be the full thickness. So that goes on bottom. Now we're most likely going to end up with a decimal answer here. It's not going to come out to be a nice, neat fraction. So we'll multiply 80 times 3/8 divided by 100. So to do that, I'm going to do 80 times 3. To do 3/8, I'm going to do times 3 divided by 8. Oops, by 8. Hit equals, that's 30. And then divided by 100. So we get 0.3 inches is what we would have to penetrate to get a 80% penetration. If I have 9/16 inch steel and we penetrate 3/8 of an inch, let's find the percent penetration. So we're finding the percent, so it's blank over 100. The full amount is the 9/16, so that goes on bottom. The 3/8 is the amount of penetration, that goes on top. To make this work, you either have to convert your fractions into decimals, equivalent decimals, which isn't bad. You just do 3 divided by 8 is 0.375. 9 divided by 16 is 0.5625. Or you can use some parentheses. I'll use the parentheses since I know you guys can do it with the decimal form. 100 times 3 divided by 8 gives us that cross multiplying. Now to divide by 9/16, we have to put the 9 divided by 16 in parentheses. So we divide by, and then in parentheses, 9 divided by 16. We get 66.67. So 66.67 out of 100, or 66.67%. What do you think? Not bad. Another application of these proportions is your amperage. I grew up using voltage settings on a welder. They discovered that amperage is way more important and it's way easier to calibrate if you have amperage settings. So most of your modern welders have amperage settings on them. The relationship is 1/1000th of an inch of penetration per amp. So what that does is it's going to be 1 amp over 1/1000th of an inch. And we're going to use that in a proportion to find required amperage or penetration for a given amperage. So let's say we need 3/8 inch penetration. Find the amperage, find the amps. So 1 amp, again, 1/1000th of an inch. And just like we said before, the units have to stay the same on bottom. So it's inches on bottom. My other inches, my 3/8 of an inch also has to go on bottom. And then so 1 times 3/8 divided by 0.001. So 1 times 3 divided by 8, then divided by 0.001 gives us 375 amps. Or if I ask you to find the penetration, for 150 amps. Well, again, 1 amp equals 1/1000th of an inch. Again, whatever units are on the left side have to match the right side, so we have amps on top, so we have to put the amps on top on the right side as well. And we'll cross multiply and divide. 0.001 times 150 divided by 1 is 0.150 inches. Now, some of you are probably recognizing a pattern, or if you do this often enough, you'll see it's just moving the decimal point 3 spots is all it really is. So as we're dealing with metallurgy, one of the other important quantities describing metal is something called an elastic modulus. It describes how much a metal is going to stretch or compress under a given force. To understand elastic modulus, though, there are a couple of things we need to talk about. First, one is stress. The stress on any sort of a support member is the load over the area that it's applied, often called a cross-sectional area. So the simplest way to think about this is if you have a beam in your house and you have a post supporting that beam, and the load on the top of that post is 40,000 pounds. And let's say that this beam is a rectangular beam, 4 inches by 6 inches. We can find the stress on that beam or on that post by first finding the area. How do you find the area of a rectangle? Length times width, right? It's 4 inches times 6 inches. 24 inches squared will be our area. So the stress is the load, 40,000 pounds over 24 square inches. Giving us 1,666.67 pounds per square inch, or PSI. Typical load for wood, by the way, non-graded wood is 1150 to 1200, but you can have 1600, 2100, or 2400 PSI grades of lumber. So if you get this calculation, it's telling you have to grade up to a higher grade of lumber. You can't just use standard number 2s. Let's say you have a round post. A 4-inch diameter round post, and it has to support, let's do 80,000 pounds. So again, we start off with the area of the post. Well, the area is going to be the area of a circle with a 4-inch diameter. Of course, when we find the area of a circle, it's pi times radius squared. So how do we find the radius? What's the radius going to be here? 2 inches, half the diameter. So this will be pi times 2 squared. So pi, you can either just use 3.14, or most of your calculators have a pi key. I'm going to use 3.14 times 2 squared. Gives us 12.56 square inches. That's the area. So then the stress is going to be my load of 80,000 pounds over my area of 12.56 square inches. So 80,000 divided by 12.56 is 6,369.4. And again, that's pounds per square inch, PSI. Steel, by the way, typically you're looking at 60,000 PSI as its max, so that's nowhere near maxing out the steel post. So for you guys, where's that going to be? Well, it's kind of bumping back a semester or two, but if you're looking at rigging, if you have a steel cable, and let's say you have a 1/2 inch diameter steel cable, steel is rated at 60,000 psi. So that is 60,000 pounds per square inch. We need to figure out what is the maximum load that can be supported on this 1/2 inch cable. And of course, to do that, we have to find the area of the cable. So again, it's a 1/2 inch diameter. The radius would be 1/4 inch. So the area is pi times 1/4 squared. I would probably just convert the 1/4 to 0.25. Just to make it a little easier to work with. So pi 3.14 times 0.25 squared. We get 0.19625 is our area. To find the max load, then, we know that this is, as a rate, 60,000 pounds over 1 square inch. How much is that going to be for 0.19625 square inches? We cross multiply and divide. So 0.19625 times 60,000 divided by 1, we get 11,775 pounds. Now you're probably going to be working with some safety margins where they're probably going to say never go over half a max load. They'll usually never go over 80% of max load at the very most, but there's your max load. The other quantity that's necessary to understand elastic modulus is something called strain. The amount of strain is the elongation over the original length. Often written as delta L over L. So if I have a 20-foot cable and I put a load on it, we're not concerned about the size of the load right now, but that load stretches the cable 3/4 of an inch. The strain is the stretch, 3/4 of an inch. I'm going to write it as 0.75 over the length of the cable. Now, the length is given in feet. We need to convert that to inches. So it's 20 times 12, or 240. So the units are going to be inch per inch, or usually they just don't put a unit on the strain. So 0.75 divided by 240, and it always ends up being a really small number, 0.003125. That is the strain. So what that is the elongation per inch of length. So we can use that. If we're going to use a longer cable but support the same weight, let's say we need to swap that out and we're now going to use a 35-foot cable. We need to know how, for the same load, we need to know how much that cable is going to stretch. Well, we can use a variation of this formula. Delta L is going to equal the length times the strain. So the length, again, is 35 feet times 12 inches per foot. It has to be done in inches. Times that strain of 0.003125. So 35 times 12 is 420 inches times 0.003125. It's going to stretch 1.3125 inches. Why is that important? Well, because if you're in a spot where that weight has to be suspended over something, you need a clearance, you need to know what it's going to sag, what it's going to stretch the cable. So an elastic modulus allows us to find the stretch without actually loading up the cable. Elastic modulus is stress over strain. So if you know the stress and you know the strain, you can just divide them out. Most of the time we don't know those, however, so we know that stress is load over area. Strain is delta L over L, so if we're dividing by it, the delta L is going to go on bottom and the length on top. So it's the load times the length over the cross-sectional area times the change in length. So if we have 16,000 pounds on a 3/4 inch cable, that is 20 feet long. And our cable stretches let's see here. We're just going to go 1.72 inches. Find the elastic modulus. So applying this formula, little e, by the way, is used for elastic modulus. We have the load of 16,000 pounds times the length. Well, again, the length is in feet. Everything else is in inches. So it's going to be 20 feet times 12 to convert it into inches. Then over the area, well, we have a 3/4 inch diameter cable. The radius will be 3/8 of an inch. So the area is going to be pi times 3/8 squared. So 3.14 times parentheses 3 divided by 8, close parentheses, squared. Give us we're going to go 0.436. Will be close enough for this. Inches squared. So that's what we're going to put in for our area. And our elongation is the 1.72 inches. So I don't need to have the units in there. So on top, we'll do 16,000 times 20 feet times 12 inches per foot. So 3,840,000 on top. On bottom, 0.436 times 1.72, 0.75 basically. And we divide. 384, 1, 2, 3, 4, divided by 0.75. We get 5,120,000. That is in PSI is the units on that. If we did the units out, that's what we come up with. Sounds huge, but the elastic modulus of aluminum is 10,000 PSI, so this is actually weaker than aluminum. 10 million PSI for aluminum, I should say. Steel is 29 million PSI. So let's go the other direction with this. We're going to find the elongation in a 30-foot one-inch diameter steel cable under a 40,000-pound load. So I'm going to find the area of my cable here first. 1-inch diameter means, of course, a 1/2 inch or 0.5 inch radius. So that area, 3.14 times 0.5 squared, is going to be what, 0.78? 0.785 square inches. So that's our area. Now here, we know the elastic modulus, E, is 29 million PSI. So this formula up here, we're going to adjust it a little bit. Rather than E equals, so that formula up above was E equals load. For load, we actually use F for load times length over area times change in length. Now we're trying to find the change in length. So the formula just adjusts a little bit. Come on. The change in length is the load times the length of the cable over the area times the elastic modulus. So we had a load, 40,000 pounds, times a length, 30 feet. Again, remember, we have to convert that to inches, so times 12. Over our area of 0.785 times the elastic modulus of 29 million. So 40,000 times 30 times 12 on top. Oops. We get 14,400,000. On bottom, 0.785 times 29 million. We get 22,765,000. We divide that out. I'm going to leave off the 3 zeros on the end of each number. Do still have to have the 2 in there, though. We get 0.6325 inches. So that's 0.6325 inches that cable is going to elongate. So again, whatever you need for clearance on bottom, you need to shorten it up by 0.6325 inches. Any questions there? So there is one question on the homework that asks you to find the diameter of the cable required if you have a limit on how much it can elongate. Rather than take 5 minutes to do that example, I'm going to leave it up to you to try to figure out. On the quiz, I actually put it on the quiz for 2 weeks from today as an extra credit question. So we can go over it before the quiz, but I don't want to load you up with any more. I want to give you at least a few minutes to work on stuff to get started and ask questions. Anybody have any questions on anything? Okay, so you got your last few minutes here to get started on the work.